Now, initial value problems, cases, general solutions, again, I.V.P, I.V.P, uh, I.V. problems, initial value problems, basically is ordinary differential equations plus initial conditions. Now, second order, I should have two initial conditions. This is going to be the first initial condition. This is going to be the second initial condition. The first initial condition at y, the second initial conditions at y prime. So those are the two initial conditions. And as we said in first order, I can use those two initial conditions to find the constant in my general final answer. Okay. So this is the general solution that we get. And I should point out that for second order ODE, for homogeneous in the second order ODE, I should have two solutions. Y1 and Y2. And this is the linear combination of the two. So this is what we call the general solution. It's the constant, this is the first phase, this is the second phase. Now, to find the two constants over here and C1, C2, I need the two initial conditions. Now, the two initial conditions differentiate y and plug the y at the first point, plug y prime at the second point, and you will be able to find C1 and C2. Now, I'm going to talk about this example over here. Now, solve the initial value problem, y double prime plus y equals 0. This is homogeneous and linear ODE, and I want you to find the solution for the I.V.P at y0 equal to 3 and y prime 0 equal to 9. Now, we just learned from previous example that we just discussed, just a couple of slides before that, y1 cosine x and y2 cosine x are solutions. And the general solutions can be written in that form. C1 cosine x plus C2 sine x. So this is going to be your general solution. Now, since I do have initial value problem, I have two initial conditions, one for y and one for y prime. Basically, you need to substitute 0 for x over here, and you will be able to find C1. Since I have y prime, so differentiate this y and plug for x equals 0 to find the other constant. And in some cases, you might need to solve the two equations. Some cases you get those right away. Some cases you have to do some elimination or substitution to find two constants C1 and C2. And now if you do those two, you will find out that C1 equals 3 and C2 equals -2, and this is the particular solution, the very specific solution at the two initial conditions. So this is the general solution, and this is the particular solution at the given initial conditions. Now, just go back over here. Now, cosine x and sine x. Now, we mentioned that those two are two solutions, and as I mentioned just before, if you multiply anyone by a constant, for example, cosine x multiplied by any constant, then the new one is going to be a solution. So r cosine x and, for example, sine cosine x are two different solutions, or it's one. In fact, it's going to be one. We're going to consider them as one family. So in ODEs, we are talking about families. Cosine x and sine x are two different ones. I'm not talking. A general solution of ODE, if I do have two solutions, y1 and y2, and they are not proportional. Not proportional means if you take the quotient of the two, it cannot be a constant. If the quotient is a constant, means they are two proportional, means they came from the same family. For example, sine x and 7 sine x. For example, sine x and 8 sine x. The quotient is a constant, so they are proportional, means we are talking about one thing. But if you look to sine and cosine, they are different because if we take sine over cosine, gonna get tan, cosine over sine, gonna get cotan. It's not constant, so they are not proportional. They are not proportional. So if y1 and y2 they are not proportional, we call them cases, and in some other case we call the fundamental system of solutions. So to be basis, the first y1 should be a solution, y2 also should be a solution, and they are not supposed to be proportional, means the quotient is going to be not constant. Not constant. I'm going to just, this is just exactly what I mentioned, the quotient one way or the other way around. This is another way how to write it down about linearly independent, or sometimes called linearly dependent. It's going to be the same concept. When we call y1 and y2, we call them linearly independent. Linearly dependent if the quotient is constant, if they are proportional. Means y1 over y2 equals some constant, means y2 is equal k times y1, means y2 depends on y1. So this is what we call them dependent. So we try some cases. It's going to be the same concept as we did before. Just This is just try to formulate a basis of solutions. We call them apices if the quotient they are not constant. Not constant. Sometimes we call them linearly independent. Okay, just take this one. Verify that y1 and y2 are solutions of the linear homogeneous ODE. Y delta prime minus y equals. Basically, you have to prove that this one is a solution, or to prove that this one is a solution. For this one is a solution, differentiate it twice, substitute in the ODE. The same thing for the second one. Now, you're gonna find out that the first one is a solution, the second one is also a solution. Now, do they form a basis? Basically, take the quotient y1 over y2 over or y2 over y1. In either case, you'll find out that y1 over y2 is not constant because the quotient is going to be function of x, which means y1 and y2 they are not proportional. They are not proportional. It means they are linearly independent. So they form a basis. So y1 exponential x and y2 exponential 2 for negative x, they form a basis for all. On the other side, guys, if you look e for x and 7e for x, the quotient of those two is either 1 over 7 or 7. It's constant, to mean they are proportional. They are proportional. They don't form a basis because they are dependent. They are dependent because they are dependent on each other. The quotient of the two is constant. Okay. Now, right now, we are ready to find a basis. As I mentioned, guys, over here, we're going to talk about homogeneous linear. For homogeneous linear second order ODE, I should have two bases. I should have two bases. Now, in case one of them is given,